Last time we looked at how light bouncing from a mirror looked like to a person traveling on a train versus to a person sitting on the tracks and watching the train go by. We saw that in both cases light traveled a distance d in the y direction to and from the mirror, but in one case, in the case of the passenger on the train, the light traveled no horizontal distance, whereas in the case of the passenger viewing the train, the light in addition traveled a distance of 2b, where b is equal to 2 times the speed of the train times the time it took the light to reach the mirror. From this we see that here the light traveled 2d, and here the light traveled 2 square root of d squared plus b squared. So for light to have been observed to travel at the same speed in both of these frames, it means that the time in both of these frames must have been different. And here we will calculate just how different that time is. So recall again that in the first frame light traveled 2d, and if you divide this by time you get the speed of light in the first frame, and in the second frame light traveled the square root of 2b squared plus d squared. And here we have a different t prime, and we know that these two speeds must have been equal to the speed of light. Actually, this is 2t because it bounced to the mirror and back. Likewise, here is 2t prime. So now let's do a little bit of algebra to see how exactly these times are related. First of all, we're going to cancel these 2's, and we're going to bring out the d from inside the square root. So let me write this as d over t is equal to square root of b squared plus d squared over t prime. Now we're going to say this is equal to d times the square root of b squared over d squared plus 1 over t prime. So what I did here is I took the d squared from within the square root and brought it outside, and in the process divided the b squared by it. And now the d's cancel on both sides, and we have t prime over t is equal to square root of 1 plus b squared over d squared. And continue on the next page. So t prime over t is equal to square root of 1 plus b squared over d squared. Now let's recall that b is equal to the speed of the train times the time t prime that the observer that's stationary on the ground sees it. And d is equal to the speed of light times the time that it travels. So this is the distance from where the light starts the mirror is d, and b is the horizontal distance the train travels while that light is moving to the mirror. So let's make these substitutions. We have t prime over t is equal to square root of 1 plus v over c squared times t prime over t squared inside the square root. So what do we do now? Well, now let's just square both sides. So the square root goes away here, and we have this squared. So we can do a little bit more algebra to solve for t over t prime. And I'm actually not going to do it all here, but I'll just give you the result, which is that t prime is equal to t times 1 over square root of 1 minus v squared over c squared. And in these few lines of algebra, we have derived the relativistic time dilation. So this says that t prime and the time observed by the observer sitting on the ground is going to be actually different from the time observed by the passenger in the train. And this is exactly how much different that will be. So this is the first amazing effect from relativity, that time passes at different rates for observers in different frames.